Welcome everyone to a new video. Today we're doing a very nice question and it goes like this. A to the n plus 1 minus a plus 1 to the n is equal to 2001, and we need to find a and n, and they are natural numbers. We're gonna showcase the power of modular arithmetic, and if you're not familiar with it, here's a quick review. If I take 4 and I want to take mod 3, well, 3 goes in 4 one time and leaves a remainder of 1. Another example, let's say 12, and I want to take mod 8. Well, 12 would be 4 modulus 8 because you can divide 12 by 8 and you'll be left with a remainder of 4. We also have negative numbers when we're doing modular arithmetic. For example, I can have 4, which is congruent to, well, negative 4 modular 8. And this means that we still have 4 left to get till 8. Generally speaking, when I say a is congruent to b modulus n, well, this means that n divides a minus b. Like 3 divides 4 minus 1, 3 divides 3. 8 divides 12 minus 4, which means 8 divides 8. And 8 divides 4 minus 4, that's 4 plus 4, that's 8. And this is the general meaning of mod. So here I'm interested in a couple of modular forms. They are a plus 1, and one of the factors of 2001. 2001 factors into 3 by 23 by 29, if I'm not forgetting it. And, well, I'm going to take modulus 3 of this. And let's see why. A n plus 1 minus a plus 1 to the n. Well, that's congruent to 0 modulus 3. Why? Well, 3 divides 2001 and it doesn't leave any remainders. Now, since we're working with modulus 3, all numbers will either be 0, 1, or 2, because we can reduce them to that. So our first case here to consider is that a and a plus 1 are both 0 modulus 3. But this is impossible. If a is congruent to 0 modulus 3, then this part is 0 plus 1, which is 1. And 1 to any power will always be 1. And this congruence will never be satisfied. And if a plus 1 is congruent to 0, this means that a is congruent to negative 1. And negative 1 to any power will never be 0 modulus 3. So we ruled out two cases. A is congruent to negative 1 and a is congruent to 0. Now, negative 1 is congruent to 2 modulus 3, and so we have ruled out all the cases except 1. So a must be congruent to 1 modulus 3, so 1 to the power of n plus 1 minus 1 plus 1, that's 2, to the power of n, that's congruent to 0. Now 2 is congruent to negative 1 modulus 3. And this is helpful because 1 and minus 1 could cancel out and produce the 0 that is needed. Now 1 to any power is just 1. And this is satisfied when it's 1 minus 1. So this has to be a positive 1. Negative 1 is positive when we have an even power, and negative when we have an odd power. So we have found a very important condition, that n must be even. So now we have our first piece of information, and that's n is even, and that will be helpful later on. So let's take modulus a this time. A is congruent to 0 modulus itself because it divides itself. A to the power of n plus 1 minus, this will be 0, plus 1, that's 1, to the n, that's congruent to 2001 modulus a. Now, of course, we can forget about this, and 1 to the n is just 1, so negative 1 is congruent to 2001, and moving this around, we get 2002 is congruent to 0 modulus a. Now, why is this helpful? Well, this means that a divides 2002, and since 2002 is 13 by 11 by 7 by 2, well, a has to be one of those. And now we have a finite set to choose from. So now we have two pieces of information based on mod 3, one of our factors, and mod a, one of our terms. Now we need to take mod a plus 1. Well, a plus 1 mod a plus 1 is just 0. A mod a plus 1, well, since a plus 1 is 0 modulus itself, a must be congruent to negative 1. So this will be negative 1 to the power of n plus 1 equals to, or is congruent to 2001 modulus a plus 1. Now we have this piece of information and it's even. Then that means n plus 1 right here, that's odd. Negative 1 to an odd power is negative 1. Moving things around, we find that 2002 is congruent to 0 modulus a plus 1. Now this is very interesting. It means that a plus 1 divides 2002 and a divides 2002. Let's see what that means. Now we're going to use these two. A divides 2002 and a plus 1 divides 2002. Well, this number could be rewritten as 13 times 11 times 7 times 2. And the only way we can create two factors that are consecutive is that if we take 13 and take 2 by 7. That's 13 and 14. 13 and 14 are consecutive and they divide 2002, then they must be a and a plus 1. You can check for yourself. So plugging in some simple values, you'll find that n equals 2 will satisfy your mom. So trying simple values like 1 and 2, you'll find that n equals 2 will satisfy your mom. No! Trying simple values like 1 and 2 for n, you'll find that n equals 2 is a solution. How do we prove there aren't more solutions? We need to take a restrictive modulus. What do I mean by that? Well, let's say we take 14, this term right here, and we take mod 8. Well, 14 is congruent to 6 modulus 8, which is congruent to negative 2. And if I take negative 2 and I square that, I get a 4, which remains a 4 in modulus 8. And if I cube this, I get a negative 8, which is 0. And if I keep increasing the powers, I'll keep getting zeros. Now, this is helpful because here I want to check every case above n equals 2. And here, with this sort of structure, you'll be able to find it very easily. Now we're going to take n values greater than or equal to 3, and we're going to take the mod 8. As we saw before, 14 with n equals 3 and above will zero out. It will be a 0. 13 is, well, 5 modulus 8, which is negative 3. 5 is congruent to negative 3 modulus 8, and you can see this easily if you do 5 minus 3, which is just 8. So negative 3 to the power of n plus 1 is congruent to 2001. 2001 is 1 modulus 8. It will leave a remainder of 1. Now we have negative 3 to a power equals 1. Let's try to figure out a pattern for the powers of negative 3 mod 8. Taking negative 3 and squaring it, we get a 9, which is 1 modulus 8. Increasing the power, we'll get another negative 3. Increasing the power again, we'll get a 1, and so on. So we have a very simple pattern. For n values, for powers odds, we'll get negative 3. And for even powers, we'll get a 1. Now, we know that n is even, and so n plus 1 is odd. But since it's odd, we'll always get a negative 3, and therefore this congruence will never be satisfied. This proves that we have only one solution, and that is n equals 2 and a equals 13. Thank you for watching.